Hello. Today I'll be analyzing the constant velocity motion of a ping pong ball rolling along a ping pong table. I'll do this by first using a program to track the ball's movement along the table, and then I'll construct a computational model to predict the ball's motion along the table. Finally, I'll compare the two sets of data, the predicted motion from the computational model and the observed motion, to see how the results match up. Here's the video of the motion of the ball. As you can see, I've tracked its position during every frame of the video. One important thing to note is my coordinate system. I've made the origin of the coordinate system to be the starting position of the ball, and I have the ball moving in the negative x direction without any real movement in the y or z directions. I was able to get the proper scale for the graph because I knew the diameter of the ping pong ball and was able to use it as a reference point where it was 40 millimeters during the video. Now that the motion is over, I can take a look at the plotted graph of the motion. As you can see, it looks like it has a pretty constant slope. However, there are 5 breaks in this video. This isn't due to the ball just slowing down randomly in the course of the movement, but rather due to the faulty setup that I had. The room I was in was dark, and so the camera was not able to perform to its full capacity, and therefore it repeated several frames during the video. But this shouldn't mess up the overall movement of the ball when we compare it to the computational data, which I will show you now. As I said, the computational model is based almost entirely on Newton's second law, where the final velocity equals the initial velocity plus the net force over the mass times the change in time. For this constant velocity lab, we know that the initial velocity will equal the final velocity. Because of this part of the equation has to be 0. We know that the mass of the ball is not 0. We know that the change in time is not 0. So we have to assume that the net forces acting on the object are 0. In our code, let's run through it right here, we take that into account. We still put in all the relevant data. We put in the ball's mass, which we know to be 27 grams based on the standard mass of a ping pong ball. We put in the ball's initial position, and we put the ball's initial velocity based on our observed plot of the data. The initial position is just the position of the ball at the 0 point, at the 0 time. The initial velocity we can get based on the first 2 points, just getting the distance over the time for them, the average velocity of that point. Going back to the computational model, the actual calculations of the code happen in this portion. We have while the time is less than 0.7 seconds. We have 0.7 seconds because that's the duration of our observed motion. And then we put in all the relevant data for this part. The net force I've just shown you is going to be 0, but we still include that here, and then we include Newton's second law to update the velocity. Because the net force is 0, this part doesn't matter, but in the future it'll be much more important, so we have to keep this here so that we remember that. The final position of the ball won't be the same because it's just the initial position plus the velocity times the change in time. The velocity is constant, but this will still get a new position because the times will cancel out and we get a new position. Finally, in the loop, we have to iteratively update the time so that each time it goes through, it does it based on a new delta t. Now, once we get all this code down, the computational model should run like this. Here we see the model for the ball's motion. It's moving in the negative x direction at a constant velocity, and this is how it would move if no net forces would be acting on the ball. Now let's compare it to our observed results. Here is the plot of both data sets. The computationally predicted motion from Python is shown in red, whereas the points that we observed in our tracker are shown in blue. The slopes of both are very similar, and the lines of their positions are almost perfectly in line. The breaks are still there in the observed point from the faulty camera, but they still line up very similarly to that of the predicted motion. Now that we've seen that my observed motion is moving at constant velocity, or almost constant velocity, we can ask what forces were acting on the ball to give a net of 0. Well, there's only 2 that are really important in this case. One is friction and one is gravity. The gravity is moving in the negative y direction and the friction in the positive x. The axes don't really matter. If I had the coordinate system in another plane, it would be different, but for the purposes of this experiment, I'm keeping the ball moving in the negative x direction. Now the force of gravity will be balanced out to a net of 0 by the force of the ground up on the object, up on our system. The force of friction, however, doesn't have something acting against it, but rather is just so minimal because of the ball's rolling motion where it doesn't really play that big of a part, keeping our object moving at constant velocity.